Hello and welcome to another video of Antennex where I show the capabilities of the wireless connector. Today I would like to show you the FMCW application that we have developed in which we can do physical layer performance testing of FMCW radars. Currently I have a Texas Instrument evaluation board, which is an FMCW radar chirping from 60 to 64 gigahertz. With pulses of approximately 40 microseconds long. And you can see that there's only DC and USB going into the DUT. So there's no RF signal being fed towards the DUT. It's all being generated inside the device itself. And we would like to capture how much power is being transmitted by this one and do the physical layer testing of the performance of this FMCW radar module. This signal is what we are going to capture and analyze in combination with an oscilloscope. So just with a simple Ethernet connection between the reverberation chamber and the oscilloscope, we will capture the data of the chirp and we will post-process that to get, for example, the chirp linearity, the power spectral density, but also chirp rate and those kind of metrics. So at the side of the chamber, we have the external path which we will calibrate with the external calibration, which consists out of a mixer to downmix the signal from the FMCW radar, which is operating at 60 gigahertz, to a maximum of 6 gigahertz, which the oscilloscope can capture. So the mixer is being fed by the DC power. There is the signal going towards the oscilloscope, and there is an LO signal coming into the mixer to do the down conversion. And then we have at the other side the DUT feed-through panel where we have just a power going towards DUT. There is no RF signal going in the DUT. It's all being generated inside the DUT itself. So for this setup, we will be using the FMCW application, which you can access from the main screen. So we'll click on FMCW and that will open actually the results window. Before we can do a measurement, we have to do a calibration. And this you can access via the calibration menu. In the calibration menu, you will see that there are actually three parts of the calibration, which is the chamber calibration, the antenna efficiency, and the external equipment cal. And what these three factors mean, you can actually see in the information section. So you can see that the green part, that is the chamber calibration. That is the losses in the chamber itself, including the DUT loading. So the DUT will introduce extra losses in the chamber, which we have to calibrate for. And this calibration can be done in two ways, or by using a spectrum analyzer combined with a calibration module inside the chamber that will generate a signal. And we can do it with a vector network analyzer, in which we just do a simple S11 measurement from which we can extract the chamber losses, including the DUT loading. The second part is the antenna efficiency, and that's the antenna efficiency of the reference antenna. So the DUT will be transmitting through the chamber losses and it will be captured by the reference antenna, and that antenna efficiency can be uploaded at just an antenna efficiency file which is already known before, or you can also calibrate that by a VNA measurement, which is the same as doing an efficiency measurement using the chamber, of which we have an earlier video. And then the final part is the external equipment calibration. That's all the electronics from the reference panel to the oscilloscope. And in this case, that is a downmixing circuit because we have a 60 gigahertz signal being transmitted by the DUT, and we have an oscilloscope that can only capture a maximum of 6 gigahertz. That can be calibrated by, for example, a VNA measurement. So you can just do a simple VNA measurement of that mixing conversion loss, and you can upload that as a file on the chamber to calibrate for that. I already calibrated the external part and I saved the file, which I can go to load file. And then I go to the USB stick where I have this file on. I will just click on it, click on open, and now my external calibration file has been updated. You can check your calibration files as well via the information screen, where you have a table, a graph, to visualize what your current calibration files are, and there you can check if the uploading has been done correctly. Then we can continue to the setup of the measurement. To be able to do a measurement, you will have to tell the system at which conversion frequency you're working at. So I first have to enter the local oscillator frequency, which is at the moment 59.7 gigahertz, and I'm using an upper sideband configuration. Then you can go to the reverberation chamber settings. Well, in a continuous wave signal measurement, we usually use approximately 100 stir positions, but an FMCW signal already contains so much more information than a continuous wave signal that with just 4 positions, we can already do a very accurate estimation of the performance metrics of the FMCW radar. So that's what I'm using during this demo. Then you have the oscilloscope settings. In this case, you just have to make a simple Ethernet connection between the chamber and the oscilloscope. And then the chamber can take full control over the oscilloscope to do the measurement. And then finally, you have the acquisition settings where we configure the start and the stop frequency. Well, the DOT chirps from 60 to 64, so I take that frequency band with a little bit of margin to both sides. And then we configure the time, the start time and the stop time of the chirp at the oscilloscope. This one has a pulse length of 40 microseconds, so again, I take 40 microseconds with a little bit margin in front of behind the pulse. And we will be using the default post-processing settings. Now we're ready to measure, and we can just click on measure to start the measurement. And then in just a couple of seconds, you can see the results of your measurement. So first we will have a spectrogram. In the spectrogram, you can see that the chirp indeed covers a pulse of 40 microseconds, chirping from 60 to 64 gigahertz. From this, you can extract the linearity of your pulse, the chirp rate, the duration, and the total power that is being transmitted during the full chirp. And you can also go to the power spectral density, in which you see the power spectral density over frequency of the chirp. That's it.